Okay, 2021 free response problem number 3. So this is our first one in the non-calculator section. Let's remember that here, everybody. Okay, so we've got a company designing spinning toys using a family of functions given by this right here. C is a positive constant. Okay, got it. And the figure above shows a region in the first quadrant given to us by this function right over here. Y is equal to C of x, Cx times x, times the square root of 4 minus x squared for some C. Okay, gotcha. Each spinning toy is in the shape of a solid generated when a region is revolved around the x-axis. So this thing is spinning this direction. Sounds like it might be a volume problem, and that means this is going to be dx anytime we're spinning something around a horizontal axis of revolution. Okay, gotcha. So 3 parts to this problem. Each one of them took a decent amount of time and space. So part A right here, find the area of the region in this first quadrant bounded by the curve that they've given us there. Y is equal to C times x, and then we've got the square root of 4 minus x squared. So that's what we're looking for, and they tell you here a specific value of C we're supposed to use, which is going to be 6. So we're looking for the area of this region. The way we're going to do this, I'm going to need to do this on a separate page, but I'll at least get started right here. That area is going to be a definite integral. The function itself, y, is going to be cx and then multiplied by the square root of 4 minus x squared. We're taking all that with respect to x. So that setup is pretty easy, but it's the limits of integration that are the first challenge to this problem. We can tell right here this thing begins at x is equal to 0, which you also could tell, I think, guys, by looking at the function itself right here. And if this x right there were equal to 0, that's how you would get y equaling 0 overall. So we've got 0 for our lower limit of integration. Coming up with the upper limit of integration, that is going to come from the second factor of this function right here. So if the square root of 4 minus x squared were equal to 0, we would just solve that, square both sides, and get a 4 minus x squared equals 0. X squared is 4. X is going to equal plus or minus 2, but we're looking for a positive x-intercept right here, and x equals positive 2 is where this region ends right there. So that's going to be our setup. Oh, and I should have noticed here, they told us to let c equal 6 here, so I could probably have gotten rid of that c right there and put a 6 there. So that's the integral that we have right here for part A, but they want us to go ahead and evaluate that, and that was a little bit tougher than I thought it was going to be at first. So let me write that down again. So for part A, our area was a definite integral, we said, from 0 to 2 of, it was 6x, then times the square root of 4 minus x squared. I'm going to go ahead and pull that 6 here, the constant, out in front of the integral here and make that 6, let's do that in blue, make that 6 times the integral of x times the square root of 4 minus x squared taken with respect to x. Now, without a calculator, we have to go ahead and evaluate that. To do it, you might recognize 2 distinct parts to the integrand right here, and we've got a second degree function here and a first degree term right here. That smells like u substitution to me, everybody. So we're going to let u equal our radicand of 4 minus x squared, something we did a lot back when we did u substitution in 5-7. We'll do the derivative of u then, which is going to equal a negative 2x dx, and I don't want that negative 2 there, but I did need the x and the dx there for my secondary substitution. So I'm going to divide out that negative 2 and get a negative 1/2 du is equal to x dx. Okay. So what does that do for us, guys? This area then is going to be 6 times a definite integral, and I'll leave the limits out for right now. Our primary substitution comes right here. That is going to be the square root of u. And then the secondary substitution, the x and the dx right here, gets replaced by a negative 1/2 du. So I'll put a du at the end, and I'll pull that negative 1/2 all the way out in front, and then we're going to multiply that by 6. All we're missing now is limits of integration, but let's remember, the 0 and the 2 that we had a moment ago were values of x. Now I want them to be values of u. So I'm going to take 0 and plug it in right there for x. 4 minus 0 squared is going to get me 4 for a lower limit of integration. And something weird happens here now. I'll take that 2 and put it in here for x. 4 minus 2 squared is 0. So our limits of integration, when we change them from x values into u values, now all of a sudden are backwards from what you might expect them to be, but no need to panic about that. All right, what are we going to do here, guys? We're going to multiply the negative 1/2 times the 6 to get a negative 3 out in front. And then let's antidifferentiate the square root of u. Now, of course, that's u to the 1/2 power. So when we antidifferentiate, that's going to become u to the 3/2. And then we divide by that new coefficient or multiply by its reciprocal right there, which is 2/3. And we'll evaluate all of this from a 4 on the bottom to a 0 on the top. Now, I'm a little bit concerned with the fact that we have a negative coefficient out here. That's going to become a negative 2, but I think the fact that the limits are backwards means this is going to work out okay. Let's plug the 0 in for u first. 0 to any power is 0, and then minus 4 to the 3/2 power. Ooh, we've struggled with this year, guys. I want to remind you here that 4 to the 3/2 power means the square root of 4, and then we're going to cube that result. So that's a 2 cubed, which is going to end up equaling an 8 here. So we end up with a negative 2 times a negative 8, and we end up with positive 16 for our answer here. And I feel pretty good there that that answer worked out to be positive because, of course, it's a region in the first quadrant right there. So, went the wrong way with that. All right, gotcha. So that was part A. Yeah, find the area of the region. Got it. So part A is done. Okay, part B. They've told you here, this was nice of them to save you a little bit of work. They did the product rule for you there already, guys, and they've told you the derivative is this messy quantity right over here. And it says for a particular spinning toy, the radius of the largest cross-sectional circular slice is 1.2 inches. Now, guys, if we go to this solid in the graph up above, if we flip that thing 180 degrees, it would kind of make a shape here that would look something like this. And the largest radius would probably occur, I'm just guessing right here, at a spot right about there. That would be taller than any other radius that I could draw here, or here, or here, or here. So it's really just that one in the middle that I care about. Now, they tell us that that radius is 1.2 inches. Okay, good to know. And we want to figure out what's the value of C for that particular spinning toy. Okay. Now, what we're going to need to do here, guys, I believe, is use an important idea. If this red radius that I have drawn right there is actually the highest possible value that R can be, that would mean that we would have a horizontal tangent to this curve right at that spot right there. That would mean that my derivative, dy dx, would equal 0 at this particular point here. We're going to use that to figure out x using this derivative right here. So let me go ahead and write this out, guys. I'm going to go here. Let's put part B right over here. So our derivative then, dy dx, was equal to, and I don't think I remember this, all right, c times 4 minus 2x squared up in the numerator. 4 minus 2x squared, and then down in the denominator, that, although it doesn't really matter, I'll show you why in a second, is going to be the square root of 4 minus 2x squared. Did I get that right? No, I'm sorry, just 4 minus x squared. Okay, and there we go. We want to know what's going to make that derivative right there equal 0. Well, the first thing we would do here, guys, is multiply both sides by the denominator, but this times 0 on the right side is just going to wipe out. Or another way to look at it, the only way that a fraction like this derivative can ever equal 0 is if the numerator all by itself were equal to 0 as well. Now, what we're trying to do in part B here, guys, is find the value of C, and they tell you now, guys, that C is a positive constant. The fact that C is positive means that C can't equal 0. So we can divide both sides by C now, that cancels, and we just get 4 minus 2x squared would equal 0. And let's jump over here to the side and do a little bit of quick math. So we'd now get 4, that was ugly, is equal to 2x squared. Divide out the 2 and get 2 is equal to x squared. And then we'll get x is equal to plus or minus the square root of 2. But again, since we know everything exists in the first quadrant right here, we can ignore the negative. So x is equal to the square root of 2 tells us the x coordinate of this point right here, guys, root 2. Now, with all that in mind, that tells us something important. At this ordered pair right here, we now know both the x-coordinate and the y-coordinate. The x-coordinate we just found is the square root of 2, And the y-coordinate comes from the length of that radius. So 1.2 is our y-coordinate. And now that we know the x and the y-coordinate at one particular point on this curve, we can plug those values in for x and y and solve for c. So let me write this out again here now, guys. Y is equal to, that was cx times the square root of 4 minus x squared. That's what we have right there. I'll make sure I got that right. Yep, got it. And now we know that this curve right here contains the point square root of 2, 1.2. So let's put a 1.2 in for y. We don't know what c is. The x here becomes the square root of 2, and then we multiply that by the square root of 4 minus, and I'm looking for x squared, which is right there, 4 minus 2. Okay, so 1.2 is equal to, I'm sorry guys, that root x right there should have been a root 2. My mistake right there, because we had already solved for x. So we have a root 2 here times another root 2, which is just going to make a 2c, and then we'll divide both sides by 2, and that should give us our answer now of c is equal to 0.6 for this particular spinning toy. And I believe that was all they wanted us to do in part B. What is the value of c for that toy? And yeah, we came up with that one. Okay, C was one that when I did this problem on my own the first time before I've made this video, I got an answer and I thought, that's pretty ugly and complicated. I think I probably made a mistake. And then I went and checked and no, that was it. So, all right, let's run with C. For another spinning toy, meaning different from what we just did in part B, these two things are not the same. So ignore the value of C now that we came up with in B. Now the volume of this new spinning toy is 2 pi cubic inches. They want to know the value of C for that particular spinning toy. So what we're going to need, let's do this, guys, for part C is a volume equation. Now, what I'm hoping you guys might have realized already here is that your cross sections here are going to be circles. There's no gap here, everybody, between the original region and then the axis of revolution. So that means that our cross-sectional slices are all going to be circles, and we're going to follow the good old formula here for area of a circle. So I tell you what, actually, before I do V equals, probably should have talked about this. Area of a circular cross-section then is going to be pi times your radius squared. And the radius is going to be given to us, forget the 1.2, that doesn't apply anymore. The radius is given to us here, guys, by top curve minus bottom curve. Whatever y is, that's your radius, guys. So the radius then is c times x times the square root of 4 minus x squared. So what we now need then is, again, I'll move volume down a little bit further right here, area written as a function of x is going to be pi times this whole radius, cx, times the square root of 4 minus x squared, bracket, squared. So pi times r squared. Now this can be simplified at least a little bit here, guys. That 2 gets applied here to the c and to the x and to the square root right here. So our area function would be pi, gotcha, times c squared times x squared, and then the square root of 4 minus x squared squared just becomes 4 minus x squared. So that's kind of ugly, but that's where I'm at right now for a of x, and I think I'm going to leave it like that rather than do any distributing. Let's talk about y. Volume then, everybody, is going to be the definite integral now of whatever your a of x function was, which was right here. But I'll remind everybody, we can pull constants out in front of this whole thing. And pi is a constant, and so is the c squared. So pi c squared is going to come out in front. And that's going to leave us then with x squared times the 4 minus x squared, and that I am going to go ahead and distribute. So that's going to leave me with an integrand here of 4x squared minus x to the 4th, and we're doing that integral all with respect to x. And the only thing I'm missing are my limits of integration, but if we go back to this, it's this same region here we talked about before, guys, that starts at 0 and ends right here at 2. Nothing has changed there. So an integral from 0 to 2, and we were told now that for this particular spinning toy, the volume is 2 pi cubic inches. So we're going to set that equal to 2 pi And we're going to have to solve this thing for c. So this is kind of an unusual problem right here. Okay, this is what we have here, guys, and I think we're going to go ahead and evaluate that integral. The one thing I'm going to do right now, though, real quick, is just divide both sides here by pi. That'll just allow me to cancel that, and the pi here are gone. So now we're going to end up with c squared, and let me start a bracket now. Antiderivative of 4x squared is going to be a 4/3 x cubed, minus the x to the fourth now anti-differentiates to a 1/5 x to the fifth, all of which gets evaluated from 0 to 2, and all of that has to equal 2 now that we've divided the pi out. Still got some work to do in those brackets here, guys. So this is going to be c squared times, all right, 2 cubed is 8 times 4 is going to be 32 over 3, minus 2 to the fifth is 32, so that becomes a 32 over 5. All of that now, oh, I'm sorry, and then with the 0, putting a 0 into a polynomial function is just going to get a 0 in both cases. So I'm done with my left side now. All of that is equal to 2. And right now is about the time when I was doing this problem before that I thought, oh, maybe I'm doing this wrong, because this looked like a lot of grunt work that they were making you do by hand without a calculator. But no, this is right. All right, with denominators of 3 and 5, our least common denominator is going to be 15. So I'll multiply the first fraction by 5 over 5, the second one by 3 over 3. So I get c squared times, now without a calculator, I don't know, 32 times 10 is 320. Half of that would be 32 times 5, 160 over 15. Minus 32 times 3 is 96 over 15. Gotcha. All that is equal to 2. Let's keep going. C squared now times, and 160 minus 96 is going to get us 64 over 15. Okay, all of which is equal to 2. Now that fraction doesn't simplify at all, so let's start working on getting c by itself. Let's multiply both sides by its reciprocal, 15 over 64. Those cancel out. And then, well, I'll do this one at a time here. C squared then is going to equal, that would be a 30 over 64, which simplifies to a 15 over 32, and then we'll take the square root of both, well, really there too, of both sides of the equation here, and end up with c is equal to, and they were okay with us leaving our answer as the square root of 15 over 32. Now again, there would be a plus or minus right there, but they told us in the original problem here, guys, that c had to be a positive constant, so no chance that this ends up being negative. So guys, when I did this problem the first time, I thought, oh, that was ugly, that can't be the right answer. No, that's the right answer, guys. C is equal to the square root of 15 over 32. So that was a pretty tricky problem, I think. Each of those three parts, I think, was an interesting spin, that's a pun, on kind of the typical area and volume problems that we had. So they didn't actually ask you to find a volume. They gave you a volume and asked you to solve for C, and kind of a similar thing going on in some other ones. So tough problem there, number 3. Hopefully that makes some sense now that we've gone through it.